Okay. And yeah, you're saying what? Yes. Cosine 2x. Okay, so that is not going to present any problems. But one part of this is going to make this difficult. So what technique do you need to finish it off? So, what?
Said some kind of trick thing.
Actually, it gets worse than that.
Is it like an integral rule?
Yes.
It's like chain integral or something? Or?
No. Which term causes the problem?
2x.
Everything is easy to do except one piece.
Is it the fraction part? No, that's not.
No. There are no fractions left.
1 2x.
Yeah, because you have x cosine x, x sine x. How do you do something like that? Anyone remember from Calc 2?
Been a long time.
I'm going to guess integration by parts.
Yes.
That's what I was thinking.
All right.
But only because it's written in Charles. He's honest.
Minus points for you.
They're with those points for spotting that error in the notes.
Yeah, integration by parts. So you can. So it's u dv is uv minus integral of v du. So you would use u is x.
That's where I got the chain integral rule from. What a chain rule is part.
X minus sine x dx. So that means that du is just dx, and v is going to be the antiderivative of this, but that's just sine x plus cosine x. So the result is going to be u times v, that's x sine x plus cosine x, minus the integral of this du. So we get sine x plus cosine x dx, but this can be integrated directly, so you won't have any problem with that. You just have to apply integration by parts once, whereas if there had been something nastier in there, like say x to the 10th sine x, you'd have to apply integration by parts 10 times. Well, there are formulas like in the back of any calculus book where we've worked all of that out.
But there's like a shortcut too for that, or
Yes, there's a method that lets you work out all the constants correctly. I never bothered learning it. All right. So anytime we have solid that can be defined as the difference between two planes, determine which one is the top, which is the bottom, you'll just integrate their difference. Other than that, it's worked out in the usual way. The whole question is, and something to keep in mind, of course, for exam problems, what is it you're actually going to have to integrate once you got it all set up? Now, for these problems, I consider the setup to be an important part of this, because once you carry out the integration, well, that's really more of a 168 kind of thing. Okay. So, where are we at on time here? Okay. All right. So one other thing I want to touch on. Back when you first started learning about integrals, single variable case, you learned they had certain properties you can take advantage of when you're working them out. Or it can also help you estimate integrals. Okay. So all of these are properties that come from single integrals, but they apply in a similar form to double integrals. Okay. So first property, linearity. Anytime you have integral of a sum, just like the single integrals, you can break it up to sum of the integrals. This is sometimes lumped under linearity, but in Marsden it's called homogeneity. If you have double integral of constant times a function, just like a single integral, so you can pull the constant out. Okay. No, I'm not expecting you to know these names. Alright. I'm saying if one of the books mentions them, then you'll know what they're referring to. Additivity. This one I mentioned earlier, actually. You have a region D that's the union of two regions, and this would extend to if it's a union of more than two regions. Then, to get the integral over the entire thing, you can just integrate over two separately, if that's convenient. For example, that region that you work with in problem 4 on the exam, that's the window pane, the rectangle plus a half circle. You might as well integrate your function over a rectangle, then integrate it over a half circle, and add the results together.
You managed to do that?
That's not part of a problem, though.